In the previous chapter, we studied renormalization, and we saw that renormalization amounted to imposing a certain set of matching conditions that allowed us to eliminate the parameters of the model for parameters that would be measured in experiment. So these matching conditions or renormalization conditions were all phrased in terms of the Fourier transform of correlation functions. So the idea is that we first have to compute the position space correlation functions, then we have to Fourier transform them, and after we've done the Fourier transform, we can apply our matching conditions or renormalization conditions. It would be simplest if we could simply compute immediately in Fourier space, so that we write down a set of Feynman rules for which we can actually calculate the correlation functions directly in momentum space. So in this chapter, our goal is to write down such a set of Feynman rules that will allow us to calculate Fourier space correlation functions. And the way that we will achieve this translation of the position space Feynman rules to a set of momentum space Feynman rules is just by motivating them with a well-chosen example. So the example that we're going to study, we're going to consider this Feynman diagram. So we propagate from event x1 to event x2. We'll consider a Feynman diagram with two vertices. We'll place the first vertex at x and the second vertex at y. So if we want to write down what is the expression corresponding to this Feynman diagram, well, we've got two vertices. So we'll need a minus I 4 factorial g, and then we'll have a factor of z squared. Remember, because now we've written our Lagrangian in terms of the physical field, and this will be squared because we've got two vertices. Then we need to integrate over the positions of both of those vertices. So we'll have a d4x and a d4y. Okay, let's now start filling in all of the propagators. So we need a propagator to take us from x1 to x. So we'll have a propagator from x1 to x. Then we have three propagators going from x to y. So we'll have g, x to y, cubed, because we've got three propagators going from x to y. And then we need a propagator going from y to x2. The only thing left now is to calculate the combinatoric factor. Well, there's no closed line, so we don't need to worry about that. There are no equivalent diagrams. We have a single diagram, and there's no equivalent vertices. The vertex at x is distinguished from the vertex at y because x vertex connects to the external point x1, while the y vertex connects to the external point x2. So those two vertices certainly are not equivalent. But the three lines that travel from x to y, this is three lines that share the same endpoints. So we would have a factor of 1 over 3 factorial. Good. Okay, now to get the momentum space Feynman rules, we're actually going to plug in what these Green's functions are and do the integrals over x and y. So let's do that. Okay, so we've got the minus I 4 factorial g c squared squared over 3 factorial. Then we've got an integral d4x, an integral d4y, and then we've got the g of x1 comma x. So how do we write that? Well, this will be an integral d4 p1 over 2 pi to the 4. And then we've got I z minus 1, that's our propagator for the physical field, over p squared minus m squared plus I epsilon. And then we have an exponential e to the minus I p1 dotted into x1 minus x. Now, this propagator goes between x1 and x, and we've associated to it a momentum p1. So I'm going to draw another Feynman diagram over here. And this is the momentum space Feynman diagram. And we'll figure out exactly what this is as we go along. But what you can see is, so this line over here that I've now traced in blue, that's the line that goes from x1 to x, and that's the line that we've associated a momentum P1. So on this Feynman diagram, we're going to imagine that there is a momentum P1 flowing along that line. Good. Okay, let's keep going. So now we need to write down 3 propagators from going from x to y. So we will have an integral d4 P2 over 2 pi to the 4. We will have an I z inverse e to the minus I P2 dotted into x minus y over P2 squared minus m squared plus I epsilon. And we can imagine that a momentum P2 is associated with the top line going from x to y. Then we've got another propagator, integral d4 P3 over 2 pi to the 4. We've got an I z minus 1 e to the I P3 dotted into x minus y over P3 squared minus m squared plus I epsilon. So now we've given a momentum P3 to this line in the Feynman diagram. And then we've got one more propagator, an integral d4 P4 over 2 pi to the 4. Again, I z to the minus 1 e to the I P4 dotted into x minus y over P4 squared minus m squared plus I epsilon. So now we've assigned a momentum P4 to this last line going between x and y. And then we've got one more Green's function to take care of, an integral d4 P5 over 2 pi to the 4 I z inverse e to the I P5 dotted into, what is it? It is y minus x2, but it's minus I P5. There should be minus I P3. There should be minus I P4. And then this is over E5 squared minus m squared plus I epsilon. And we'll put a P5 sitting there. So I haven't really done anything. I've just plugged in the expression that you know for the Green's function, okay? So no big deal. But notice what this already suggests is, instead of labeling the endpoints of lines, we'll be talking about the momentum flowing along each line. So now let's consider the integral over d4x. So we're now going to perform the integral over d4x. And let's just see where all of the x dependence is. Well, we've got an integral d4x, so certainly that we have to take into account. Then here there is some x dependence in that exponential, in this exponential, in this exponential, and in that exponential. So what do we have? Well, we've got an integral d4x, and now I'm just going to collect together these exponentials. So we've got an e to the I P1 dotted into x. Then we've got, in fact, let me write this in a slightly nicer way. I want to write this as x dotted into. Then from the first exponential, we've got P1. From the next exponential, we've got minus P2. From the next exponential, we've got minus P3. And from the next exponential, we've got minus P4. And if we do that integral over d4x, this will give us a factor of 2 pi to the 4. And then we'll have a delta function, delta 4, of P1 minus P2 minus P3 minus P4. And what you can see is this is again that integral of an exponential giving you a delta function. So you can see once again how important this formula is. Great. Okay, we'll continue in a moment.